Hi everyone, my name is Adol Greek Kantuma, and on this video I'm going to focus on beam design. Okay, we've designed our slab already. We are going to take the values from our slab and then distribute them to the beam. Like you know that your loading is being from the slab is being distributed to the beam. The beam takes the load to the column send it down to the foundation. Okay, if that is correct. Now the values we got from our slab calculation or slab design rather, now from, if you have been following that same GA, that value we got now on panel 1, this is panel 1, on the shorter span, which is 3830, look at LX 3830. Okay, 3830 on panel 1. Now the equivalent UDL on that beam is 13.43. now this value that we got, we are going to divide it by 2. Divide by 2 now, because half of that load is being taken by this side and then half is being carried by this side. So when you divide 13.431 divide by 2, you get 6.72. okay, here too you get another 6.72. now when you go to panel, let's go down to our panel 2. okay, our panel 2 is a one-way slab, which is this. Our panel 2 is a one-way slab. Now when you are dealing with a one-way slab, you will notice that the only beam that is carrying this load on this particular panel is beam 3 and beam 4. okay, this span in beam 5 is not carrying anything from this particular panel. Now the beams that are carrying the load from this panel are beam 3 and beam 4. It's different from that of panel 1 when you are dealing with a two-way slab. okay, so for this panel 2, now what is the value we got? Now 11.73. That's the load you use on your left hand side, 11.73 on your right hand. okay, that means both left and right, the beam on this left and the beam at this right, which is 11.73. here too is same thing, 11.73. okay, now let's go to panel 3. now if you come to panel 3, which is a two-way slab, you see on the short span, panel 3 and panel 1 are actually similar. okay, they are actually similar, they have the same width and the same breadth. okay, both length and breadth are actually the same. okay, so the equivalent UDL on that beam is actually 13.43 on your short span. now the short span, which is this, now on that short span, we have two short span on this particular panel. We have this one, then we have this two, right? That's beam 1 and beam 3. That's this particular span on beam 3. So when you divide 13.431, now it gives you 6.72. You share it into 2. Now part of it, half is taken by this bin, half is taken by this bin. Okay, in this particular spans. Okay, now if that is correct, now let's go to panel 4. Panel 4 is also a one-way slab. So we have the left shear on beam/wall. Now these are the loadings. Okay, not loading, sorry. Now this is the value. Okay, now this value on the left hand side 9.1, on the right hand side also 9.1. so we share it. Now this is, we are not going to divide this value into 2 because this 9.1 is on this particular member, okay, this particular span, then the other 9.1 is on this particular span. If we assume this to be left and then this one to be right, now because it's a one-way slab, you can see this indication showing that only this beam and this beam that are carrying load, that's the beam 1 and beam 2 that are carrying load in this particular panel. Now that means that the beam 8 and beam 7 on this particular span is not actually carrying anything from this panel. Okay, that is why it is 0. It's not carrying anything from this panel. Okay, now another thing is this value 3.01. you will notice another one on T, which is 2.88. I'm going to briefly show you how we got that. Now look at this. Now we have our L beam, we have our T beam. Now let me briefly explain what an L beam and T beam is. Now if you look at this extreme end here, what shape do you see here? It's an L shape. Sorry, my system is actually slow. Okay. What you get here is also an L shape. Okay, now check this out. On beam 2, what you see here is a T shape, right? Here too, what you see here is a T shape. Okay, now that is how to understand what an L beam is and a T beam is. So that means our beam 1 is actually an L beam, our beam 2 is actually a T beam. Okay, our beam 3 is also a T beam. So I'm going to briefly show you how to come up with this particular value of 3.01. Now because this particular beam depth is actually 450, that is why our value is 3.01. now when this value changes, or when this depth of beam changes to maybe something like 600, now mind you, this value is not going to be 3.01 when you are designing for a beam of maybe 230 by 600. Okay, it's going to change from this particular values we provided here. Now you can see this is 300 by 230 by 24, which is the density of concrete multiplied by the factor of safety. Okay, look at this plaster. Okay, which is 300 by 230 by 450. Now if it's a 600 beam, definitely you know this value is going to change. For 600 beam, your bottom depth is going to change. It will definitely no longer going to be 300. Okay, you need to take note of that. And here too. Okay, come back to your T-beam. The same thing. Okay, when you are dealing with a 600 beam, it could be 600 beam, it could be 750. You know, the depth of beam actually is not a constant value. It is not always 230 by 450. It could change depending on the loadings. Okay, it could change. So from your design, you get to know that. Okay, if that is correct. Now for that of T-beam of 230 by 450 beam, now is what, 2.88. That of L-beam for 230 by 450 is 3.01. Now these are the values we are going to use here. Okay. Sorry, that was actually a mistake. Okay. Let's come back to our drawing. Now, after getting, now since we now understand where the value 3.0 is coming from, 3.01 is actually coming from 2.88, where it's actually coming from. Now you sum this value, your equivalent UDL with this, you sum this with this, and that's how we got 9.73. okay, same thing applies everywhere. Okay, that's how we got all of these values. Okay, now okay, let me bring your mind back to this. Now look at this. Now you notice that the loading on this particular beam is definitely going to be greater than that of this particular beam. The reason is because this beam is actually carrying load on both sides. Like it's carrying this panel, it's carrying part of this panel too. Here it's carrying this panel and it's carrying part of this panel. Okay, so that's why this beam is actually carrying more load than the external beams. Okay, the internal beams are actually carrying greater loads than that of the external beams. So by the time you sum your 6.72 plus 2.88 plus 11.73, you get 21.33. okay, now the next thing you do is to design your beams, since we have gotten all the values that we need. Okay, now for beam 1, this is your beam 1. okay, for beam 2, this is your beam 2. Now you can see there's actually no column on this, like it's completely on this particular beam and on this particular beam. Okay, it's acting as a point load. Okay, what we'll do now is to design this beam using RCD 2000. Now I'm only going to design 3 of these beams: beam 1, beam 2, beam 3. You can try it yourself. I just want to make this design as brief as possible. If you enjoy what you are seeing, why not give it a thumbs up? Click on the bell icon to get a notification whenever I post videos. I post videos on daily basis, sometimes weekly basis. Subscribe to this channel. It's actually free. Just click on subscribe button, the red button down below, and subscribe for free. Okay, let's come back to our RCD. Now, to design, what you do is to click on this your beam. Don't open it, just click once and drag the file, drop it on your Dropbox. Okay, if your system is 64-bit, your system is 32-bit, you don't need Dropbox. Just double click and it will open for you. Okay, the next thing you do is to type your T, you enter, F, enter, output name, let's say beam design, enter, no password, job reference is just job number. Okay, /job/002. Okay, design engineer. Okay, J dot key value. Design date March 2020. Okay, enter number of beams. Now we have 3 beams because I want to design 3 beams, but on this GA number of beams are up to 8. So if you want to do the entire beams, you enter 8 instead of 3. I just want to make this video very brief. Okay, so enter number of beams 3, concrete 20, steel 410. Okay, and your miles steel, that's your steel rope, okay, is 250. Okay, beam ID, beam 1, going to design beam 1 now. Press enter number of supports. Now on this beam 1, we have 1, 2, 3, 4. Now we have 4 supports. 4. Enter number of members. Now we have 1, 2, 3 members on beam 1. Member 1, 2, 3. Okay. 3. Enter grid support, grid number. Okay, enter support grid number. Now for this beam 1, this is beam 1. On this beam 1, this is the grid 1, 2, 3, 4. Okay, so you type 1, you double space, 2, double space, 3, double space, 4. You can see it's written. This one is very, very interactive. It says 2 spaces for each. Okay, it will guide you on whatever you should impute. That's why I will always advise this for beginners before you can go into the external file method. Okay, what is the width of your beam? It's a 230 beam. Okay, what is your BF? Now on this BF, now see that of an L beam, it has a value of 0.07. This 0.07 is actually gotten from a very simple formula, which I may not show you on this video. You can get the reinforced concrete design book by Victor Oyenuga. It will help you a lot. You see most of these formulas from there. It's a practical design book. Okay, 0.07 times the maximum span, then plus your breadth of web. Okay, now 0.07 on that beam 1, you will notice that the maximum span is 3830, although all the spans are actually equal. So on a beam that you have different spans, okay, you pick the highest value, you multiply by 0.07, then you plus your 230. That will give you your BF. That's when you are dealing with an L beam. Okay, when you are dealing with an L beam. On a T beam, the difference is going to be in this particular value. Now this one is going to be 0.14 instead of 0.07, that of T beam. Okay, that is how to get your BF. So since our beam 1 is actually an L beam, now our BF is going to be what? 498. Now the height, that's the depth of the beam, is what? 450. Now the breadth of the depth of your flange is what type? We have different kinds of support. Okay, for pin, cantilever, and free, we are going to use 0. Okay, for fixed or built-in support, we are going to use 1. Okay, down below I'm going to leave a link how you can get the manual to this design. Okay, you can contact me and you get this manual for this particular package. Okay, enter end support type. Now 0, the load on that particular support. Now let's come back to this one. Now there is no load acting on this particular support. Now that is why we are going to put 0. Once there is no load, definitely there will be no moment. Okay, because moment is force times perpendicular distance. Now on this particular beam 1, there is no any load acting on the beam, on the support directly. Okay, there is no load acting on it. So this is the first support, which is 0, the load 0, the moment 0, and then the end support, okay, is actually 0, the load is 0, and then the moment is also 0. So I'll press enter, 0 space 0 space 0, and enter. Now this beam is asking for the serial number. We can just say 1. What is our span for the span and the load? Okay, for span 1, input the value for span 1. This is the span 1. Now this is our span 1. Okay, now on span 1, what is the span? 3830. Our span 1, 3830. Okay, what is the load that is acting on span 1? I'm going to type in 12.1. Okay, now we don't have a triangular load, we don't have a trapezoidal load. Okay, no point load also. So I'm going to press enter. Beam 2. Number of support in your beam 2 is, now we have 2 support. Okay, 1 span. We have 2, 1 span. Okay, that's 1 member. Enter grid. Now on this beam 2, you notice it falls in grid 3 and 4. Beam 2, 3 and 4. Okay, so 3 space 4. Okay, what is the width, which is 230? What is the BF? That's breadth of flange. You know here this beam is actually a T-beam. Okay, so and the span is 3830, so it's definitely what we are going to use. We don't have different span, so that is definitely going to be our maximum span. Okay, now for a T-beam, this is an L-beam. For a T-beam, which is 2.88. So now mind you, we have a continuous beam, we have a simply supported beam. Sometimes this value actually changes based on whether it's a continuous beam or a simply supported beam. Okay, I don't want to go into that detail. I'm still going to design book by Victor Oyenuga. Okay, now what is the depth, which is 450? What is the height of flange? Okay, which is 150. That's the thickness of your slab. Okay, so you must be very careful. Sorry, this value is not 2.88. I picked the wrong value. Sorry, this is what I'm supposed to use. BF. Okay, breadth of flange 766. So you must be very careful when dealing with the terminal method, because once you make a mistake, you can't correct it. You have to start afresh. That's why the external file is much more faster. There is a little bit more complicated. Once you attain mastery in this, you can easily understand the external file even on your own. Okay, your HF now 150. Okay, so you must always checkmate your work. Okay, I think everything is balanced. Enter end support type 0,0. I believe you remember. Okay, what support? Is it a fixed support? Is it pin? Is it a cantilever? So those that will determine, as I said earlier on, for fixed or built-in is actually 1. For pin, cantilever or free is actually 0. So it's going to be 0. There is no load on that support acting on it directly. So, and there is no moment, okay, on this first support, on this, okay, this and this is your beam. Now enter. Okay, enter member serial number is going to be 1. What is the span? 3830. What is the load that is acting on this? Our load is 12.1. Okay, that is the load that is acting on this beam. It's 12.1. Okay, triangular load 0, trapezoidal 0, height, trapezoidal height 0, point load 0. I believe we remember. Okay, we are done with beam 2. Let's go now to beam 3. Enter number of supports. For beam 3, how many supports? We have 3 supports, right? 1, 2, 3. Which is this. 1, 2, 3. And then we have 2 span. We have 2 span, 3 supports. So enter number of supports. We have 3. Our span is 2. Okay. Now the grid is this is 1, 2, 3. Okay, that's where this beam falls. Serial 1, 2, 3. That is the grid number. 1 double space 2 double space 3. Enter. What is the beam width? It's 230. What is the flange? It's a T-beam, okay? It's a T-beam. So it's 766. 766. What is the depth? 450. 150. Okay, enter end support types. Is it a fixed support, pin, cantilever? I believe we remember. Okay, just like we did earlier. Okay, enter serial number for span 1. That is the first span. That's this first span. Okay, let's enter a serial number for it. Okay, let's say 1. The span is 3830. The load that is acting on this beam is what? Okay, 21.33. 21.33. That means the loading on this beam entirely, the 2 spans are actually uniform. Okay, so whatever we get in the first span definitely what will transfer in the second span. So the load is 21.33 0.33, 21.33. Okay, no triangular load, no trapezoidal load, no trapezoidal height, no point load. 2, that's for panel 2, serial number 2, 383021.33. okay, triangular 0, trapezoidal 0, trapezoidal height 0, point load 0. Now we are done with our design. Congratulations if you are able to get to this point. If you enjoy what we are doing, I'm still going to make a video on how to design your column. Okay, how to design your column. Now you understand how you transfer your loadings from your beam to your column. Okay, it's very interesting. It's more realistic. Okay, and stateless. Okay, now see, we have finished our beam design. Okay, what we'll do now is to check our result. Now this is beam. Let's check our result. Now this is it. You can see for beam 1, 450 by 230 beam. Okay, characteristic strength of concrete, characteristic strength of steel. These are flange width. Okay, now for bottom bars, look at 3y16, 3y16, 3y16. This is our top bar, 3y16, 3y16. Okay, for beam 2. Okay,